In this video, I'd like to continue our exploration of hypothesis testing as it relates to process improvement, or, like I like to say, a hypothesis test is just an experiment to show change. And we took a look in earlier videos on some of the introductory concepts of hypothesis testing, including going through some of the terms and how to set up the claims and what does rejecting the null hypothesis mean, and what is a p-value and how is it used to interpret the results. So I encourage you to take a look at that earlier introductory video if those concepts are new. But for this video, the specific learning objectives are going to be to identify different types of experiments a process improvement specialist would want to set up, or the different types of hypothesis tests. We'll review the different types of data that's used to make experimental claims or to set up, again, hypothesis tests. And finally, we'll summarize some of the most common types of hypothesis tests that are used in process improvement style projects. So in earlier videos, we set up this this sketch. It's maybe not the prettiest sketch in the world, but it in essence describes the theory behind a hypothesis test. The idea that you're creating an experiment where you've got typically two pieces of data, two data sets, and there's a black box, the hypothesis test itself, which is just a set of calculations that typically is performed using a spreadsheet software tool like Excel or some statistical analysis package like QI macros. And we set up the data sets with the claim or the null hypothesis to be that there's no change between the two, that they're the same. We place the data into the hypothesis test, and then it either sends a reject or an accept statement to us. If it's a rejection, that means that we can say no to the no change condition, or no to no change means that there was a change. And we're usually pretty excited about that because in the world of process improvement, we typically want to show that there was a change, where A might be current state data and B might be future state data. And there'll be some times where we'll enter the data into the black box, the hypothesis test, and the hypothesis test will accept the no change claim, or it will say yes to no change, which means they're the same. And if they're the same, well, then there's no real difference between the before and after data or data set A and B. Okay, so this is all a review from earlier videos on hypothesis testing. Sometimes the rejection, instead of it saying reject or accept, it spits out a p-value. And if we want a confidence level of 95%, we're typically looking for p-values. If we get a p-value that's 0.05 or less, it allows us to reject the null hypothesis and claim that there is a change. If it's greater than 0.05, then unfortunately we can't reject the null hypothesis. And this is set up for just about every type of hypothesis test. You grab two data sets, compare them in the black box, hope that your p-value is 0.05 or less, and then you can say that you can say no to the no change condition, or that there is a difference between the two. Okay, now in the world of process improvement, what are the things that we're typically taking a look at? It could be sample data, where A is a sample and B is a sample. It could be two population data sets, where A is population data and B is population data. It could be that we're looking at central tendency values, like the means. We want to compare means of two data sets. It could be that we are not comparing two data sets, but it's one data set to an already established mean, or maybe it's an established tolerance level or a specification limit. It could be that we want to take a look at the amount of spread or variation or variance. Every one of these different types of conditions, samples, populations, means, or variation analysis, requires a different type of hypothesis test. It's given a different type of hypothesis test name. The concept is still the same. It's always a black box. We're always setting up the null hypothesis to be the no change condition. We're looking to reject the null hypothesis. The picture that you're looking at always remains the same, but the name will be different. The name will change based upon the different types of experiments that you might want to run. The name also changes depending upon the data type that you're looking at. Sometimes the data that we are placing in the spreadsheet is continuous. Sometimes it's discrete. Sometimes the data that we're looking at isn't comparing just two data sets, it might be comparing three or more data sets. Depending upon the type of data, depending upon the type of experiment, the thing that we are comparing against, each one of these, we get a different hypothesis test name. So when people ask, why are there so many different names, or why are there so many different types of hypothesis tests, it's because there are so many different ways that we might want to set up the experiment. It's always set up with a similar format with you put data in the front end, black box shoots out on the back end, accept or reject, but the type of data and the type of statistic that we're doing the comparison to, central tendency or variation, could be different. Let's now take a look at some of those names. So I'm now pulling up some information out of the Lean Six Sigma Data Analysis Workbook, which I think is a nice summary of the different considerations for the names associated with hypothesis tests. What type of data are we looking at? Is it continuous or discrete data? Sometimes discrete, sometimes called attribute, sometimes continuous data is called variables-based data. Are we comparing populations or samples? Are the sample sizes large or small? Is the data normally distributed or not? These are all considerations for choosing a particular hypothesis test. Some of the most common test names are the z-test, which is typically for larger sample sizes, the t-test for smaller sample sizes, the ANOVA, or analysis of variance, which is a way to compare means of typically 3 or more data sets. The F-test, which helps you in understanding if there's been a change to the variation or spread or variance in your data sets. The Anderson-Darling test, which we've heard about earlier in our testing for normality chapter. We saw how Anderson-Darling tests were set up, and I'm going to put a special star by that one because we'll talk about some uniqueness about that later. And then a real popular one for discrete data. We don't spend a lot of time talking about discrete data analysis in this program, but it can happen, and the chi-square test is available for that. There's some other more esoteric ones. I won't go through each one of these in great detail. I'll instead point you to some reference articles that are on the course materials website, including a nice little decision tree diagram that walks you through all of these different considerations and then will flowchart your way to the specific test type. Know that most statistical packages will also do this when you are considering using a hypothesis test. And many of the statistical packages will determine the test just based upon the type of data that you've highlighted. It'll determine that it's continuous or discrete, that it's a smaller sample or a larger sample, and whether or not it's normally distributed or not. So hypothesis test wizards are a real aid for most process improvement specialists. But I do want to call out two esoteric ones, mostly just for fun. This is the Tukey test. It's not the turkey test. And the Box-Cox test is used for data transformations kind of outside the scope of knowledge associated with this program or this video, but I'm going to put a little star by it because one of the statisticians that it's named after, Dr. George Box, famous University of Wisconsin statistician, founded the statistics department, and a pretty large thought leader in the world of continuous improvement. So, hey, go Badgers. The other test that I called out earlier that I wanted to star and highlight was this Anderson-Darling test for normality. It's one of the most popular hypothesis tests used in the world of process improvement to help determine if a data set is normally distributed. The unique thing about the Anderson-Darling test is in the way that the test was set up, we are actually looking for a p-value to be greater than 0.05. Just in the way that the two data sets were set up and the claims were made. But I do want to call that one out because it's the one unique hypothesis test where when we're taking a look at data, we're actually looking for p-values greater than 0.05. So I put together this little slide because I think it is a great summary for the two videos together, and for anybody that is considering doing a hypothesis test. Let's walk through these test tips together. So one important consideration is, do you need to run a hypothesis test? There are literally dozens of other ways to show whether or not a change has been made between two or more data sets or one data set and an established tolerance that we're trying to hit or exceed. Whether it's comparing two histograms or looking at box whisker diagrams or just comparing descriptive statistics, mean and standard deviation to the before and after data. It could be taking a look at process capability metrics like CP, CPK, sigma levels of performance. It could be taking a look at percent in or defect rates. There are many ways to show that there was a change between two data sets, and I don't know that you always need to use an esoteric black box like a hypothesis test. That said, if you do decide that a hypothesis test is needed, then you make a claim about the data sets. And what we typically do is we state that those data sets are the same. We want to show that there was a change, but we start with the no change condition, the no change claim. We call it the null hypothesis. We want then to show with some high level of confidence that the claim didn't happen or it can't happen. We want to reject the null hypothesis. We want to say no to the no change condition. Then we determine the test type. And we just got done going through some of the common test types. Small sample sizes, t-test. Large sample sizes, z-test. Test for normality, Anderson-Darling. Test with 3 or more data sets, ANOVA, and so on. The software then will take the data sets, place it into the black box, run the equations associated with the data sets and the type of data that's being used, and it will calculate a p-value. These p-values are typically between 0 and 1, and the number that we're looking for in our p-value result is 1 minus our confidence level. So if we had a confidence level of 95% that we were hoping to hit on, it'd be 1 minus 0.95, or a p-value of 0.05 or less. So here's the bottom line. When you run the test and you look at the results, we're looking to see that a p-value is less than 0.05. If that is, then the data sets are different. We can say we can reject the null hypothesis. We're stating no to the no change condition, which means that there was a change, that they are different. P-values less than 0.05, and we're excited. A change has occurred. There is one exception to the general rule. There's always an exception, it seems like, to a general rule, and that exception is the Anderson-Darling test. The way that test is set up, we are actually looking for p-values greater than 0.05 to state that the data is normally distributed. So there's your hypothesis testing tips cheat sheet. In future videos, we'll grab some applied process improvement data, and we'll use Microsoft Excel and QI macros to run a couple of these hypothesis tests.